Welcome back, Physical Science 20. This is the last part in the PW1 section, and it deals with light. We just had finished looking at sound, and now we'll look at light and how light works. How does your body receive information? Many people respond to this question with 5 sentences, starting with sight, hearing, because light and sound provide a great deal of information about surroundings. Of the two, though, light seems to provide a greater variety of information. The human eye can detect tiny changes in the size, position, brightness, and color of objects. You can distinguish shadows from solid objects, and sometimes can distinguish reflections of objects from objects themselves. In this section, you'll learn where light comes from and how it illuminates your surroundings. So, how does light travel? Think of a narrow beam of light, such as a flashlight or sunlight streaming through a small window. It's made visible by dust particles in the air. You see the path of light as a straight line. When your body blocks sunlight, you see your outline of a shadow. And that also determines that light must be traveling in a straight line. When you locate an object with your eyes and walk toward it, you most likely walk in a straight path. This is because the light reflected from the object travels in a straight line. For objects to be visible to you, light must travel from them in a straight line to your eyes. Based on this knowledge of how light travels, models have been developed that describes how light behaves. So we kind of think of light as a light ray. Imagine being in an empty, dark room. When a small light bulb is turned on, you can see around the room and you can look at the bulb and see it. This means that the bulb sends light in all directions, of course. You can visualize light coming from the bulb as an infinite number of arrows traveling straight away from the bulb in all directions. Each arrow represents a light ray, which travels in a straight path until it reaches a boundary, such as something that it completely reflects off of, or something that could actually pass through, but gets bent if it travels in at an angle. So that's the next PW2 and PW3, reflection and refraction. After interacting with the boundary, the ray still moves in a straight line, but its direction could be changed. These principles that light travels in straight lines and its direction can be changed by encountering a boundary constitute the ray model of light. The study of light interacting with matter is called light optics or geometric optics. Okay? Sources of light. What is the difference between sunlight and moonlight? For one, sunlight is much brighter. Another important fundamental difference is that the sun produces and emits its own light, while the moon is visible because it reflects the sun's light. Everything you see fits into one of these two categories. Such objects, such as the sun, that emit their own light are said to be luminous sources, while those that you see due to the reflecting from them are called illuminated sources. So luminous sources include natural sources such as flames, fireflies, human-made devices such as TV, computer monitors, lasers, etc., etc. The luminous sources, fluorescent light bulbs, produce light from electrical energy. The other objects in the room must be illuminated. If they're not luminous, they must be illuminated. When the light from the bulb is reflected off of them, in a room with no light, it would be impossible, of course, to see them because the light has to be reflected off of them. Okay, the speed of light. So we looked at the speed of sound, how that's calculated. If you look at the speed of light and look at the history behind that, arguments that light must travel at a finite, meaning that there must be a maximum speed. This idea has existed for more than 2,400 years. By the 17th century, several scientists had performed experiments that supported the view that light travels at a finite speed. But this speed is much faster than the speed of sound, of course. Actually, measuring the speed of light is not easy because it is so fast. And especially in the 17th century. As you know from studying motion, you can calculate the time light takes to travel a certain distance. If you can travel how long it takes, you can get the speed if you know the distance between the 2 points. However, the time that it takes light to travel between objects on Earth is much shorter than a human's reaction time, so that's the problem. How could a 17th century scientist solve this? Clues from Io. Danish astronomer Ole Romer was the first to actually measure the time it took for light to travel between 2 points. Between 1668 and 1674, Romer made 70 measurements of the 1.8 day orbital period of Io, one of Jupiter's moons. So here's the Sun, here we are, here's Jupiter, here's Io. So it takes 1.8 days to go completely around Jupiter. So it's very quick moving. So you can measure how long it took for it to go from shadow to just appearing on this side of Jupiter when you're on the Earth. Okay? He recorded times when Io emerged from Jupiter's shadow. He made his measurements as part of a project to improve maps by calculating the longitude of locations on Earth. This is an early example of technology driving scientific advances. After making many measurements, Romer was able to predict when the next eclipse of Io would be. He compared his predictions with the actual measured times and found, though, that Io's observed orbital period increased in average by is that a 1.3 or 13 seconds per orbit when Earth was moving away from Jupiter, and decreased when Earth was approaching Jupiter. So when the Earth was here, it happened at a certain time during a certain day. But when Earth moved over to here, it took 13 seconds longer. Because of course the light reflected from the moon had to go an extra distance from here to here. So that difference in distance basically told them that light must travel at a certain speed, because it takes longer for light to hit Earth when it's in this position than when it's in this position. After making many measurements, Romer was able to predict, okay, so we talked about that. Romer believed that the Jupiter's moons were just as regular in their orbits as Earth's moon. Thus, he wondered what might cause the discrepancy in the measurement of Io's orbit. He considered another variable within the system, the movement and position of Earth relative to Jupiter. Romer concluded that as Earth moved away from Jupiter, the light from each new appearance of Io took longer to reach the Earth because it traveled farther. As Earth moved towards Jupiter, Io's orbital period seemed to decrease. During the 182 days it took Earth to move from position 1 to position 3, so in other words, closest to Jupiter to furthest from Jupiter, there were this many 100 Io eclipses. Thus, for light to travel the diameter of Earth's orbit, he calculated that it takes an extra 22 minutes, or 1.3 times 10 to the 3 seconds. Because the distance in space are so great, it is much easier for Romer to see these differences. Because on Earth, the distance is just too so short, and human reaction time doesn't account for that distance that light has to travel. At times, Io shown in Figure 11 is as much as 9.3 times 10 to 11 meters from Earth. Using the presently known value of the diameter of Earth's orbit, which is 2.93 times 10 to 11, Romer's value of 22 minutes gives the value for the speed of light, approximately 2.2 times 10 to the 8 meters per second. Today, the speed of light is known to be closer to 3.0 times 10 to the 8 meters per second, so light takes 16.5 extra minutes, not 22 extra minutes, to cross this region from when Earth is here compared to here. But really, that wasn't that bad as a fairly close measurement for what he had back then. Nevertheless, Romer had successfully proved that light travels at a finite speed. Michelson's measurement, although many measurements of the speed of light have been made, the most notable were performed by American physicist Albert Michelson between 1880 and the 1920s. He developed Earth-based techniques to measure the speed of light. In 1926, Michelson measured the time required for light to make a round trip between two California mountains 35 kilometers apart. Michelson used a set of rotating mirrors to measure such time intervals, and he came up with this answer, 2.99 times 10 to the 8 meters per second. For this work, he became the first American to receive a Nobel Prize.
Excuse this interruption. Any staff interest?